I tried to keep the meme density to at least 1 every 3 slides. Okay, so yeah, about me. I'm a PhD student at Cambridge working on large language models. I graduated from the Data Analytics Masters at Warwick in 2020. I also involved a little bit in sort of EleutherAI and EleutherAI, which are 2 open source research collectives in machine learning that I'll talk a little bit about later. And I'm a PhD fellow at StabilityAI, which is a startup in London that works a little bit on Stable Diffusion, which is a generative image model you might have heard a little bit about. This is like a list of research interests. Most of them are related to large language models and different things you can do with them. If anybody is interested in any of these things, please send me a message or come and talk to me. So the overall goal of this talk is to try and give an industry-informed perspective on AI research, give you maybe some new ideas about how to think about AI academia and where it's going. Probably quite useful if you're thinking about working in AI or interested in AI or ML in general. Also, hopefully give you some memes and some hot takes about these general subjects. So the first part is about LLMs, which the acronym stands for Large Language Models. Now that we've had chat-gpt, this makes it quite convenient to give a talk about large language models in 2023 because everybody, or most people, have kind of interacted with one at some point via these kind of online interactive text boxes. But essentially, the technology underlying all of these is just a large neural network of a particular type called the transformer, which you can see on the right. Essentially, it's just a stack of fairly simple blocks of neural network types, just scaled up so they're very computationally expensive and data hungry. I kind of think of them as a learned interface to data because they are quite multimodal. They can work with text, code, audio, images, video, protein sequences, more or less most things in the form of data. One thing they're probably quite bad at is like tabular data in the form of like categorical variables and stuff. But that's like one of the few areas which have not sort of been taken over by transformers in recent years. And so when talking about progress in large language modeling, one of the first things that comes up is scaling laws, which are essentially a collection of empirical observations about how the performance of these models changes when you increase the scale or the amount of data that you train them on. So I'm just I realize at this point I'm kind of assuming basic knowledge of neural networks, so if you are confused, do interrupt and let me know. But on this plot on the right, you can see the validation loss, or basically you can think of it as how well the models perform on the y-axis and the compute on the x-axis. And we can see that each of the lines here is a separate model size. So the largest one is the yellow one on the right. And you can see as you increase the size, they simply bottom out at a lower and lower loss in a way which follows a predictable line, which you can fit an exponential curve to this. And basically you end up then with a so-called scaling law. And we have lots of different scaling laws for different domains. Images, video, audio, code models, even reinforcement learning and other stuff. Sometimes these are revised. So the original scaling law from this image came out in 2020. Last year there was a paper by DeepMind which showed that actually this original one is looking at what happens if you vary the model size but keep the data size the same. It turns out that if you vary the data size as well, then you get a whole different scaling law, which kind of generally implies that people are trying to focus more on collecting more and more data now rather than scaling up model size. That's just an interesting side factor. Obligatory meme. This is more or less what a lot of ML research has come to now, which is that instead of focusing very highly on kind of painstakingly engineering your statistical model, you can just stack more layers, add more data, add more compute, and then you win, basically. And so this brings us to an observation known as the bitter lesson by one of the godfathers of reinforcement learning, Rich Sutton, in 2019, which is the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective. and by a large margin is the quote. And this, I think, neatly captures most of modern machine learning. That is, if your method can more efficiently leverage compute, then it is likely to do better. This, however, does not mean that there are like no better algorithms or no improvements that we can discover. It just means that you kind of need to take account of this trend when thinking about what algorithms might work best. An example from my own research a little bit is if we're looking at the problem of how to get a neural network to emulate or replicate a climate model. One popular approach, it basically involves Fourier transforms, discrete Fourier transforms. It turns out that discrete Fourier transforms on NVIDIA GPUs use the CUDA cores and not the tensor cores, and so they're much slower, which means that if you just use a transformer instead, which will use the tensor cores, then you get like a lot more for the same amount of compute, basically. So this is an example of taking the kind of the hardware into account in designing what algorithms work best, and taking this kind of scaling philosophy into account. This was written before GPT-3, which came out in 2020, but it also can refer to stuff like DeepMind's AlphaGo in comparison with older Go playing AIs, which relied less on scale, or protein folding methods such as AlphaFold, in comparison with older methods in that domain. One thing to note, actually, in terms of scaling laws, is that, going back to this plot, there was like quite an interesting phenomenon in OpenAI, the company that developed GPT-3, where they were like so convinced that scaling worked the best. Before GPT-3, there was like maybe not that much evidence that you could just scale up and you get like linear decrease in validation loss. But they were so convinced of this that they actually trained GPT-3 twice. The first time it just blew up and failed to converge in the loss. And so they were so convinced that they had the fortitude, I guess, to try again, despite the single training run costing like 10 million maybe. So that's like quite an interesting side story. Another meme. The top of the curve here shows like, I don't know, average ML scientist in academia trying to design some custom algorithm to solve their particular domain problem. And on the right, we have the perspective of just use GPT-3. If you just ask the model to solve some problem for you, it will do that. And I've noticed this be true for quite a lot of things, like even generating unit tests, making tabular data, solving like simple reasoning problems, a bunch of different tasks work pretty well with that. And now, because we are computer scientists, we can talk about some engineering challenges of scale, which are quite interesting in their own right, separate from like the ML. First one is things like parallelization. How do you actually distribute a machine learning model with, let's say, 175 billion parameters, each of which is float 32 or float 16, across however many GPUs you have, each of which may only have like 40 gigs of VRAM. And this can be quite complicated. In this diagram, you see at the top, on the y-axis, GPUs 0 through n-1. The green is the optimizer states, because when we're training a large neural network, we need a particular optimizer which stores for every single parameter in the model the exponential moving average of gradients and squared gradients. And so basically this means for every parameter you need like 3 optimizer parameters. So this is just like increasing the memory cost of training by 4. And so this makes it even worse. This diagram here is an example of how you can basically, it's called sharding. Maybe in this case you would have every single layer, only one layer per GPU, and then when you compute your forward path through your neural network, you simply delete and recompute things as necessary to keep things in memory and pass stuff between GPUs. It gets quite complicated, but it's an interesting computer science problem. Another one is quantization. There's a recent trend of changing like the bit type of the parameters in a neural network from, like, let's say, float 32, which is pretty standard, or float 16, down to even float 8, or things like people saving in int2 or int4, which are quite interesting. And this requires like a lot of engineering stuff to maintain the stability of training, make sure that nothing blows up. Determinism is a very interesting one. It turns out, even if you set all the random seeds consistently and have everything like in a Docker container, or everything is like as consistent as possible, but you simply move your code to a different GPU cluster, then the results will be different. And this is because of things like floating point addition being non-associative when it's like split across GPUs and stuff like this. It gets very annoying. And then this gets even worse when you do things like elastic scaling, which is like when you dynamically, during training, add or remove numbers of GPUs, which is like mostly used as a way of keeping high utilization. And then there's like robustness, making sure that training itself like converges and doesn't suddenly spike, like no floating point underflows or overflows, please. But yeah, these are just some of the interesting engineering challenges you can have. I think now we can talk a little bit about, I should mention, so all of these challenges combined are like a reason why cutting-edge ML papers these days increasingly require serious research engineering contributions, and the number of authors on highly cited papers is increasing to, let's say, maybe average of 10 to 20, often, even in academia or large collaborations, partly because you need now serious research engineering expertise. And so now we can look at some of the research landscape and industry trends in AI, and what have these factors I've been talking about for the past 10 minutes or so actually done to research. And so as a result of this, over the past 3 years or so, since 2020, the transformer has taken over many different domains. You can see in this plot, compared to 2020, now in 2022, we now have transformers. The domains that transformers are being used in is now much more diverse. So images, audio, bio, like protein folding, and video as well. And the downstream effects of this kind of creates serious problems for academia, because if you need such significant compute, data, and engineering resources, then it becomes hard for many computer science departments to actually fund anything significant. It means there's a greater importance of engineering skill, particularly HPC-related stuff, as I was talking about before. It means there's greater industry investment in general into scaling large models, putting in engineering and compute effort into AI training, all that kind of stuff. It also means that a lot of NLP research has kind of devolved into quirky GPT-3 facts, as some people describe it, which is basically different ways of maybe prompting the models. Whereas maybe 10 years ago, these same researchers would have been working on, like, here's my highly over-engineered custom system for medical question answering, or something like this. And they would spend like 6 months on this, and it's like completely novel architecture. Now it's just like, how can we best prompt GPT-3 to give us the answers to these questions? And this kind of results in a deluge of prompting papers and small papers, which maybe isn't that useful, because the counterfactual value of releasing some paper like this is maybe quite small, because somebody else could just do it in a few months if you didn't do it. Another feature, interestingly, about large language models is the emergent features issue, where many capabilities sort of suddenly emerge at a certain scale. So let's say maybe at 20 billion parameters, your models consistently up to there do badly on solving arithmetic benchmarks, like giving you the correct answer to what is 54 plus 129. And then suddenly, if you go to like 50 billion, it does really well. This is like the kind of dynamic we see in a lot of tasks. It's called emergent features. It does make it very difficult to do good research on a lot of things when you're limited to below a certain scale, because you never know, if you just increase the scale, maybe just everything works and it's all fine. This figure here shows the emergence of outlier features in the weights past the magic, so-called magic, 6.7b per outer number for a particular quantization technique. What else? Yeah, and so as a result of all these trends, we have this issue in ML where academia is maybe struggling to adapt. Often kind of moves at a glacial pace, has limited resources, and in some ways suffers from an outdated model of peer review and publication. As a result, kind of struggling to acclimate to new trends. One thing I've kind of noticed, for example, is that a lot of the top NLP research groups in academia in the UK are like still not really doing that much stuff with transformers, because like maybe they have some kind of bias where they think because they don't have the resources to do it, well, maybe transformers aren't that useful to work on after all, etc. And in general, if you ask somebody in academia versus somebody in research like Google Brain or something about transformer scaling and stuff, there'll be like a kind of often a difference in opinion where academics are maybe concerned about the prospects for scaling. Can machine learning really afford to run projects which cost more than 1/1,000,000th of a Manhattan project or more than 1% of CERN's annual budget? Surely it would be too expensive, even if it represented another large leap in capabilities to actually spend more than that to scale up GPT-3 to achieve such a trivial thing as human-like performance on many different tasks. Many researchers in academia, you kind of feel like they feel like such a suggestion is absurd and refutes the idea of scaling machine learning research further, and the field will be much more productive if instead we just focused on research which can be done by an impoverished PhD student on a laptop. This is like the general kind of hot take that I have. And so in some ways this is sort of related to like a just world fallacy. In my experience, there's like a bit of a blind spot in ML academia to this trend, which I think is partly because academia has kind of limited resources to train large transformer models. But the universe isn't necessarily fair, and it can just be true that making significant progress on towards more capable and robust AI systems does require more resources than the average CS department can afford. And another factor towards this dynamic, I suppose, might be that it's hard to see what the cutting edge looks like in academia. And private models are significantly better than chat-gpt. GPT-4 is a thing already. People I know have tested it. It is like the private frontier is significantly ahead of the public frontier. And this trend will only increase as more and more industry labs are moving towards publishing less and releasing less models. And meanwhile, if you were to plot a graph of where all the most cited papers in NLP or other domains of fundamental machine learning are coming from every year, so it does seem to be that the graph, the section which comes from industry is increasing, and academia seems to be decreasing, which is in many ways kind of sad. We have a tweet from Jan LeCun here, which is making fun in the third point of structure discovery, which is this, I guess, approach in machine learning, which has been pretty common throughout, particularly academia, for maybe 20 plus years, where people, when they're faced with a particular problem, they try and get algorithms to, get highly engineered algorithms to discover the structure in a particular problem. They get some algorithm custom designed for this particular problem, and then they take this structure and sort of hard code it into their models. Sort of the current paradigm of scaling large language models or other large models is basically kind of a refutation of this, where you get models which just discover the structure themselves, and then your highly over-engineered thing is kind of redundant in a lot of ways. A classic example of this might be computer vision. Pre-2010, a lot of people were working on these things called filters, which you might know if you've seen image processing or anything, which are they would hand design a filter which was optimized to detect curves or something like this. And then when convolutional neural networks came along, they just learn the curve filter themselves, and then you don't need anything which is hand designed. And this is on the industry side. OpenAI saying, we think the most benefits will go to whoever has the biggest computer. And this is a list of publicly known A100 clusters in terms of size. You can see on the largest one on the left here is Meta, with just over 20,000 GPUs. I will say there are multiple clusters which are not on this list because they're private. I know of at least one at 30K, and there are like a bunch more. Yeah, so the trend in industry, as what I'm saying with this, is basically towards increased compute usage, increased scaling, and I'm trying to some of my friends are trying to work with the government to make sure that academia and other places like this don't get left behind. Now we can talk a little bit about some trends in where ML research is going in terms of like actual algorithms and techniques. The first one is incorporating human feedback into models. There's been a lot of work, so chat-gpt in particular leans on this a lot, but there's been a lot of work over the last few years by OpenAI and others on basically getting a bunch of human annotators to interact with some large model, language model particularly, and then rate their preferences over the outputs. Well, they give them two outputs and they ask them which one of these is better than the other. And they take this data set of signals from human annotators and then they use it to improve the models further. And this way you can generally get models which don't say, most of the time, horrifically racist or sexist stuff, although they can be adversarially prompted into doing so, as kind of was popular on Twitter for a while. Another trend, so that trend is going to continue, I think, as we discover more and more sophisticated ways of gaining and integrating human feedback. Another one is retrieval. So obviously a common problem with large language models is like they're bullshit artists, basically. If you ask them something, some fact, ask them to give you some fact, there's a pretty decent chance that it might not actually be correct. It'll just confidently state something that's wrong. This is often called hallucination. And I think a big trend is to try and solve this with basically retrieval, which is like different techniques of getting information from a database or a knowledge graph or other stuff like this. Another trend is towards models which act in a world. So by a world, I just mean any kind of interactive environment. This can include a web browser, as has been demonstrated recently with like transformers that browse the web for you. I believe like Cohere's CEO recently said that he wants to give a language model his credit card info and have it browse the web for him, which doesn't sound like the best idea to me. And then the final trend is like towards more synthetic data generation. The scaling laws that we have currently are indicating that data is a bigger bottleneck than model size, and so this then motivates people to work on ways of artificially generating data when they can't scrape it, particularly in specific domains. So these are like trends in research, and I think these apply to more than just NLP or natural language processing. They apply to computer vision. They apply to applications like the one I mentioned earlier about climate modeling. They apply to basically most things where you domains where you might apply cutting-edge AI to some problem. And we can look at some trends in industry in terms of like what the actual research lab dynamics are. Because of the sort of boom in generative AI and investment and stuff like that, this led to increasing competitive pressure. And this is definitely leading towards significant influence on industry researchers in Google and OpenAI and DeepMind and Facebook to publish less stuff, basically. A friend of mine has spoken to Demis, the CEO of DeepMind, and I'm pretty sure that he is planning on almost not publishing anything from now on, or like there's a lot of papers being blocked currently. And similarly for OpenAI and Google Brain. Google Brain is basically disintegrating, by the way. Like at least half the researchers I know there are being hired away by other companies or leaving. So that's not good. That's going to go well. More focused in industry on productizing and deployment. So obviously Google had their kind of code red thing, which shook up a lot internally when chat-gpt came out, and the executives wanted a competitor. And so they're sort of furiously working on this right now. And so this has generally created more focus on large companies trying to actually deploy these models as a product. This is kind of the opposite, a reversal of the trend which has been there for the last few years, where like Google and others have developed models but then like not done anything with them at all, usually because they were scared of backlash if they released the model and it said something racist, and every journalist was trying to get it to say something racist, and then they wrote hit pieces about it. But that was usually the rationale. Increasing investment in scaling, in large models is another trend. Also more startups doing research, particularly in the form of large collaborations. This includes stability AI, which I will mention in a bit. And so with all of these hot takes and in some ways depressing conclusions, this brings us to what can be done and what should we actually do given these trends. And a friend of mine likes to say, if you see a trend moving in one direction and it only ever goes in that direction, just update all the way, bro, basically. Which is that if we try and extrapolate into the future, the next 3 or 4 years, of this kind of research and what capabilities is it going to lead to? What does that imply for how academia should act for AI research and how policymakers should act for AI research? So the first one, of course, is focus on ideas which take account of scaling trends. And so this can be things like interpretability, research on large language models, or robustness, or generally things like trying to poke around in the internals or make minor alterations, which hopefully improve the safety and reliability of these models. Another one is like trying to make sure that your methods that you develop are like invariant to scale. So for example, if you're developing some highly engineered model for like AI for formal mathematics, but if you do this in academia right now, there's like a decent chance that DeepMind will come along in 2 years and like just train a large model on massive compute and solve formal mathematics. And I have heard on the grapevine that DeepMind actually has a team working on this right now. So this kind of thing is like an illustration of why you sort of need to move with this trend rather than against it. In terms of science policy and collaboration, I think we need to pool resources more between universities and startups and the government to basically have large ML first supercomputers for academics. So there's like a bunch of failure modes around this. There is like a policy proposal a friend of mine is working on in the government right now for with the UKRI for an academic ML supercomputer. But like there's a bunch of like failure modes whereby maybe they say, oh, we can buy this many GPUs, but we'll actually just like split them up around the country. This is obviously bad because then like any single institution can only train a certain size model. And you can't exactly pool the GPUs together across the universities. It doesn't really work that way. So they all need to be in one place. Secondly, like how long does it take to actually do this? Obviously, if you start building a supercomputer now, brand new from scratch data center supercomputer, it's going to take a few years to finish. And this is kind of slow in ML. So really what you want to do is go to some cloud company like AWS and say, we'll pay you like 10 million a year for 1,000 A100s, which is roughly the price that you would expect. And then they will like maintain it for you. They will spin it up quickly within a few months. And then it kind of all works as nicely. And so hopefully, if everything works out, then the UK government will have like some proposal to do this, and then academics will be able to submit jobs and training runs to a centralized ML computer. We'll see how it goes. A second point is, of course, to focus a little bit more on research engineering and technical skills. So often you see this thing where in large companies which work on all these models in their research industry labs, they're absolutely desperate for anybody who knows what they're doing with training large models or having experience on a cluster or anything at all, which isn't like something that you can train on a single GPU in 2 days or something like that. The latter is like the usual ML research experience that people get, but the former is what companies and industry labs and large collaborations often want to make progress on serious projects. And so I think it's a very exciting time to actually have an interest in ML research engineering because there's simultaneously like very high demand for this skill and very few people around who can actually do it very well. Like in many ways, there are fewer people who know how to train a large language model in practice on a cluster and deal with all the problems than there are who have read all the papers and are good research scientists and are good at doing research projects. And so as a caveat to that, often the pay is like very high and similarly competitive to research scientists in industry. And then there's another sort of glimmer of hope, you might say, in terms of like the recent swathe of open science and open source research collectives which have sprung up over the past few years. And these are a few of them on the right. The first one is like EleutherAI, which is focused. It's basically a non-profit research collective, distributed. It operates on a Discord server, which is focused on developing open and accessible large language models as a platform to do safety and interpretability research. And I'm a research lead at this collective. We published quite a few papers. We have like a bunch of industry sponsors like Stability and Hugging Face and others, which allow us to use their compute, which is nice. And we have CarpAI, which is the little fish icon. They're focused on like incorporating human feedback into models and open-endedness in general, which is an interesting direction. We are expecting in Carpa to release a very large 70 billion per hour chat-gpt competitor, essentially, within a few months. Hopefully that will go well. And then Lion, they're focused on gathering large data sets. They were the one who gathered the data set of 5 billion text-image pairs that was used to train Stable Diffusion, and generally training foundation models. And there are many others as well. Like OpenBioML is focused on biology, Cohere for AI, ML Collective, etc. So this sort of ecosystem of collectives consisting of collaborations between industry and academia has so far proven to be a decent way for like people outside of industry to get good ML research experience, a way for people outside of industry to actually have hands-on experience training large models, and make sure that if a large company is developing some, if they publish some new model and then don't release it at all, which is often the case, then we can be like reasonably sure that somebody will try and do a replication effort in one of these groups, and then hopefully release something similar within a few months. Yeah, so these were just some of my thoughts on AI, industry research, academia, where things are going. I hope you found it interesting if you were interested in ML. If not, that's fine too. But yeah, that's the end of my talk. Thank you.